everyone. Today I will talk about my work on systems for data interfaces. Data interfaces are useful and very much desired. It can help people analyze the data and draw insights. For example, if you want to analyze the COVID data, compare with writing queries in the Jupyter notebook, using this interface will let you see the trends. And when you want to change the state, you do not have to rewrite the query again and again. You can just click the drop down to select different states. Such interface is very easy to use and intuitive to see the results. People develop such interface when writing the query. A question comes to mind is, what is a data interface? Of course, there is the interface, then there is the data system. The interface will send the correct analysis in correspond to user's interaction to the system, and the system will send back the results. And take the COVID data interface, for example. This interface specifies the query, like the case state from COVID, while state equals to California. It will send the query to the data system and get the result. The visualization renders the query result. And here, the interaction changed from the state California to Arizona. The query reruns and the result will change. Finally, the layout specifies how to organize all the components together, like here. These dropdowns are laid out horizontally above this visualization. However, building even a simple interface is not easy work. Let's consider Alice's job. Alice is an engineer at a retail company. Her company has recorded the product sales data, including product, date, and the timestamp and price and store, etc. One day, Alice's boss said, we need a tool to visualize different product sales at different times. But this task is ambiguous. Like, what does time mean? It could be different dates. It can be expressed by group by date. Or it could be different time of the day. It could be expressed by group by hour timestamp. Let's say Alice choose the middle, the group by date instance. And given such analysis, Alice tries to design an interface. Let's suppose there are only 3 products, tea, coffee, and juice. Then she could just create one plot for each product. And she would end up have 3 visualizations. Or she could have one chart show the trend and have the interaction choose the product type. If she has space constraints, so showing all the 3 charts clearly is not feasible. So she chooses the one interaction and one chart interface. Although knowing JADE, there are still many design considerations. Also, the interaction, she can use buttons to lay out all 3 choices, or drop down or tab, etc. And also the visualization, she needs to decide on what chart type to use and what visual encoding it should be, like line chart, area chart, etc. She also needs to decide the layout, whether to lay out the interaction and the chart vertically like this, or it could be horizontally side by side. The design space is very large even for this simple example. In the end, let's say she picks such a design. If her company data is small, the data can reside in the browser. She can send the query directly to the database and do the aggregation on the side. So there is no network round trip at all. And the query execution time would be very small due to the small data set. And the interface will respond very quickly. However, this is not the case. Her company data is huge and resides on a remote database. The aggregation execution over a huge remote database takes time, and the network round trip to send the query over and fetch the results also takes a long while. This does make the data interface very slowly responding, which is not acceptable. She has a latency expectation for this button interaction. Alice then devotes herself to optimizing the system design. So she cannot modify her company's large remote database. She could set up a server in the middle. The server can store all the pre-computed results for different products. When the interface sends a query, this server directly sends the pre-computed results back. She worked on this for some time and implemented the system and the interface. However, later on, her boss wants a new analysis to be able to filter over the hours. Given the new analysis, she needs to redesign the interface. The interface needs to correctly express her analysis. Let's say among all the design choices, she picked the range slider because she thinks it's more intuitive to express the time range. And for such an interface, user would usually expect the range slider to be responded immediately, aka very, very fast, and the button could be a little bit slow. The previous optimization or pre-computed chart will not work since we have one more interaction changing the hour here. Thus, Alice needs to change her implementation to make sure this is the case. If we simply think about materialized view, changing a range slider requires pre-computing a quadratic number of results. This may exceed the memory constraints. So a different data structure like a cumulative data tile is needed to accelerate the query. She can pre-compute the cumulative data tile for each product on the server side. And if the browser is large, she can even put the pre-computed data tile on the client side so that the query can be answered very, very quickly. As we can see, Alice's job is to determine the analysis and design the interface and optimize the data system, then get the interface to the boss. After that, the boss may change the analysis. Alice has to redesign and re-optimize again. Each of these steps individually are very hard. For figuring out analysis, Alice needs to interpret the high-level question, which has a lot of possibilities. Then Alice has to translate the queries into programs, which require considerable programming expertise. And the analysis is evolving as the boss did, which makes it hard too. And for the interface design, it needs to consider the visualization and the interaction and the layout. And all these designs must express analysis. And for after the design, optimization is also very hard. Alice needs to figure out the interaction latency requirements, determine which data structure are helpful to the interaction, and then optimize against the execution architecture. If the resource is not abundant, we also need to consider the resource constraints as well. The whole process has dependence between each other, which makes it combinatorial hard. The analysis will affect the design a lot since the interaction design must express the whole analysis, and the design will affect the optimization. Even a very small design change can make the whole optimization totally useless. And also the optimization is only effective for certain type of design. In the end, after building a data interface, this may arouse more analysis questions from the user which will affect the analysis. The whole process is just too hard. Alice's life shouldn't be so tough. So during my PhD, I have investigated each step to help users easier create interactive data interfaces. So the first project is a data interface grammar, which represents the analysis while maintaining the one-to-one correspondence between the interactions. And PI2 is a system that can directly generate interface design from the analysis task. And PVD allows people to optimize the system backend given the interface analysis. And in this talk, I will mainly focus on the PI2 and the PVD project. So let's first talk about PI2 project. Given the analysis, PI2 is the system that can automatically generate good interactive visualization interface from example analysis. So here is the outline. I will first go through existing work and a small demo, and then talk about our problem and solution. And in the end, I will talk a bit about experiments we have done. So prior to PI2, there is no interface generation tool existing. Although there are many visualization recommendation tools like Lux, Straggle, Data Voyager, they can only generate static visualizations. And the closest work is our prior work PI. However, it can only generate a list of widgets, and it does not consider design or visualizations at all. And if we look at the tools available for creating new data interface, we can categorize them by expressiveness on the x-axis and how easy it is to create them on the y-axis. And tools like Power BI, Tableau, Metabase, Superset are easy to build interface that basically parameterize the query for data cube operations, which are common but limited. But if you want anything more complex towards the right, then you enter the world of writing a lot of code or hire a programmer. There are libraries to help, but it is still too difficult or expensive for the vast majority of potential interface that has not been created. PI2 is to generate interface for all kinds of like arbitrary analysis tasks. So let's go through a small demo. And in this case, we integrate PI2 functionality into a Jupyter notebook so that when user writing the query analysis, they could set the query to send to PI2 and we could generate the interface. For example, the user interested in what are the COVID cases around the time. So given that to PI2, it can generate such a static visualization. And later on, if a user care about what are the analysis of New York and Alaska and California during the 7 or 30 days, the user could write 3 more queries. And in Jupyter Notebook, it can generate 3 tables. But combine all of these together and send to PI2, we could generate such an interface. And if you click New York, it will change the different states trend. And you could also click the 30 days to see the different periods. And furthermore, if the user do not know how to write SQL queries, the user could resort to the natural language queries. For example, this user is interested in what are the total COVID case or deaths across all the states of US. And this user could write such a natural language query. And internally, when we select all of these sent to PI2, we could internally using LLM to translate such natural language query into a div tree. And then we could generate the interface. So give a second, we could see here is the generated interface. And the interesting thing here is that instead of using the buttons as we have seen before to set different states, PI2 found an interesting chance that we could actually click on the map chart to select the state for the first chart. And when you click on for example, Texas here, you could see the Texas trend for the last several days. And this map chart also shows the case and death distribution of all states across US. Okay, so technically our problem is given the analysis log, how can we generate good interface for users? There are 2 main challenges. The first is how to map analysis queries to interface. And this requires us to decide on visualization, interaction, and layout choices. The second is how to quantify the interface goodness. This is pretty complicated. I will just provide intuition using an example of a couple queries. Details can be found in the paper. First, we model took the queries as our part trees. And here are 2 example queries, like x and y, while a equals to 1. We omit the front clause for simplicity. And the second query is like x and y, while b equals to 10. Here, I will only focus on the highlighted part of query 1 and query 2 because that's the part that are different. And we can see these 2 part trees are rooted at equalities. Now the corresponding interface is going to be very simple because ultimately we have to execute these queries and render them. The simplest interface would be just a rendered output of queries and visualize them as a static chart. And this is what we call visualization mapping, which maps query results to visualization. But we want interactive interface sometimes, and so we introduce a new class of nodes called choice nodes to encode query difference. For instance, here, we can add a choice node, any, to choose between the 2 subtrees. And so what that means is you can choose one of the k-child and parameterize it. It will result a standard path tree that you can execute. There are many kinds of choice nodes which allows users to choose values. And we term path tree with choice node as div trees. And in the end, we represent the queries of div trees. So the nice thing about this is that this choice node can directly map to interaction. For instance, this choice node maps to a button interaction. So here, clicking on the second button would correspond to choosing the second child of this choice node. This is interaction mapping, which maps the choice node to interaction. And given the example, we can recognize that the middle tree here is a result of merging the initial pairs of trees by adding this choice node. So it went from 2 trees to 1. And now we could imagine refactoring the highlighted equality out, like here, so that we can have a tree rooted at the equality, and then you can actually map the 2 any nodes to 2 radial buttons and make independent choice for the left and the right option. So this ends up generalizing beyond the include 2 queries that we had. And these types of tree transformation allow us to generate structurally different interfaces. So here, the first interface has 2 visualizations without interaction. And the second have 1 interaction and the 1 visualization. And the right have 2 with 2 interactions, 1 visualization. And in practice, of course, we have many different types of transformation rules and types of choice nodes that we can express beyond this trivial example. So if we focus only on the right diff trees, it's vertically laid out 2 radial buttons. And I would also like to mention that we can also change it to horizontal layout like this, so that all these these 2 buttons are laid out side by side. Until this point, we can see that the tree transformation, how the tree transformation works, and how the tree structure affects the layout. Let's imagine we have a third query select C and count. This will render us a visualization where x-axis is C and y-axis is count. For instance, here the bar chart is x-axis is 1, 7, 9, 10. Notice that any is choosing between 1 and 10. So actually, we can know that we can safely map this any to the click interaction on the visualization. If you click 10 here, it will the any will parameterize to 10. And if you click 9 here, the any will be parameterized to 9. There are some subtleties that we check the interaction mapping by the domain and the schema. And then we come to the last part, how to quantify the goodness of the interface. For instance, here, we can see the drop-down and the button can both express the state attribute difference. And for such a screen size, our cost model is able to tell the drop time is better because button occupies too much space, which makes it hard to navigate and also does not leave enough room for visualizations and other widgets. And quantifying the goodness is very hard open problem. Our cost model is the best practice model, which takes into user effort, layout, effectiveness into consideration. And we are open to new models that are better, and we can integrate into our systems and take advantage of any new model that comes out. So to put all these steps together, PI to initialize the system by parsing the initial input query into diff trees, and then map diff trees to interface by mapping results visualizations, choice node to interactions, and diff tree to its layout. And finally, we cause the output interface. And then we either return it or then transform the tree further. So here comes the problem statement. Given SQL analysis, search for the diff tree and the mapping for the lowest cost interface that can express all the queries. Since the search space could be very huge, we use randomized search MCTS to find the lowest cost interface. So is PI2 helpful? The main experiment I'm talking about today is how does PI2 compare with manual design. We also do experiment on how does PI2 help with data analysis comparing with existing commotion tool text. I'm happy to chat about it offline. So to compare with manual design, we give query analysis to users and ask 12 university computer science students who know SQL to design an interface for them. And one of the analyses are COVID queries I showed at the beginning of the talk. And here I use a sketched interface. The first one has a line chart and 2 drop-downs. And the second one use the radio button, drop down, and a line chart. There are 10 more similar sketched interfaces. We asked them to compare with PI2 and they say, oh, mine is basically the same as the auto-generated interface. And the second user say, I missed something, I missed the date change, and PI2 is actually a better design. And this is the PI automatically generated interface. The line chart shows the trend COVID case along the day. And the drop-down selects between case and death and the different dates and different periods. Overall, people found PI2 is comparable to the manual design. And I have also collect the tools that the user would like to use to make their design. They are like Tableau and Visualize. Then I try to use these tools to create them. It still takes a while. For Tableau, it takes 8 minutes to configure it. And for Visualize, it takes 100 or so lines of code. Why PI2 only takes like 3 seconds? I'm not saying like PI2 is better than Tableau and Visualize, but if we have the analysis ready, existing tool still takes a while, while PI2 can automatically generate the interface within a few seconds. Furthermore, we could connect the PI2 with LLM and prompt LLM to generate a textualized dictionary. In this way, we could generate the interface from natural language queries. For example, when people ask what is the COVID cases or deaths per day, we could translate it into such a textualized dictionary like select date, sum any case or death from COVID group by date. And given such dictionary, PI2 can generate the interface shown on the right, where you could use a button to choose from case and death. So to summarize, PI2 is the first system that can automatically generate good interactive visualization interface from example analysis. And the key contributions include a compact representation of analysis tasks called dictionary and a formulation of the interface generation problem and the set of transformation rules to explore the interface design space and the efficient algorithm based on MCTS to find the optimal interface. Then after seeing how we generate an interface, I will talk about PVD, which automatically generates the backend optimization for interface when given the design. I will first talk about the motivation. In this interface, this user can click on the button to select the product ABC, and this will affect both charts. And the left line chart shows the trend of total sales, and the right visualization shows the heat map of total sales number of different days at different stores. And the range slider lets you focus on specific hour range, for example, 8 to 20. This range slider will affect the line chart. Designers, of course, care about the interaction latency. Interaction latency means how quickly does it take from user interaction to when the dependent views update. And this in practice is dominated by query execution. For instance, in this case, the button for choose a product affects both charts. Let's say user expected to respond within like median latency, say 200 milliseconds, and the slider would affect the line chart. Typically, when user drags the slider, it should update the live chart simultaneously, say like 20 milliseconds. So the problem is, if you directly post this application at your cloud database, it could be very slow since cloud database is optimized for throughput rather than latency, let alone the network type. Implementing a system to support this is hard. First, you would like a method for the designer to specify this sort of design properties. And some kind of optimization system has to take this into account. And if we look at this interface and the query details, we could let's just focus on the left chart. So this interface is doing first filtering by the product, and then just that is corresponds to the button interaction, and then we filter by the hour. That it corresponds to the hour range slider interaction, and then we go by date and the sum over the price. That is what we visualize as the line chart. In general, the hours can vary between anything that the slider can pick, and the product can be any kind of 3 product ABC, So there are many options that we could use to optimize this query. For instance, like one is that we could build a data tile. As I mentioned in the intro, you do not need to worry about what exactly it is. You can think of a pre-computed data structure that is very efficient for both filtering on the hours and also aggregating by the date and computing the size. It is super fast, but it's relatively large. And of course, sure, a data tile can help answer this portion of the query plan, but the data tile is necessarily going to be different depending on which product user picks. So we have to build like 3 data tiles for each of the products. Thankfully, in this particular case, there are only like 3. So let's say like all these 3 data tiles take like 20 megabytes, and we each of lookup takes 5 milliseconds. And we could also imagine just pre-computing the results of queries for every combination of our range and product. And there are a lot of combinations. Let's say it could take like 200 megabytes and 5 milliseconds to look up. Another alternative is to build index on our and product. We could build like a normal B tree index, let's say just very compact, like 1 megabyte. It's fast to look up in, but you need to notice that it only focuses on the feeder. So we end up need to rerun the aggregation, group by date, and sum over price every time. So cumulatively, the end-to-end time may take like 100 milliseconds. Notice that how all these require different trade-offs in terms of data structure size we need to build and the latency of using this data structure and whether what other operators we need to compute after the data structure and whether or not which data structure are applicable to different portions of this query plan. All these characteristics goes into what we need to consider in this problem, which makes it very hard. And obviously, the trade-offs also depend on the resource that you have. There is a lot of prior work on visualization frameworks like Carex, Falcon, Cube, Mosaic, and Vega Plus. However, they're limited to like a certain kind of optimization data structure, and they lack of latency guarantees. The alternative way you could try to solve this problem today in database is to cast this problem as a physical database design problem, which is given samples of queries and storage budget, choose index, partition, and materialized view to minimize overall cost. However, it has limitations that the same, like it lacks notion of interactions and there is no interaction latency guaranteed. And there are limited data structures, no data tile visualization specific data structures in database at all. And in the end, it runs in the DBMS, which is a slow path to communicate. So that's why we build the PVD system to end-to-end solve the entire problem. So PVD problem is to given the interface specification, latency, memory constraints, and the library of data structure to decide the execution plan for each interaction and the data structure to pre-compute and the cache and the data placement spanning client, server, and the cloud such that the constraints are satisfied. And also the interface specification, it can be represented as a logical query plan with choice node in expression or any choice operator which can choose from different operators. And the choice node corresponds to interactions and are annotated with latency constraints. For example, the previous interface can be specified as below, while the hours between any 0 to 24 and the product equals to any of A, B, C. And since any node corresponds to a range slider, which requires like very fast, which requires median. The while node is corresponds to like the range slider, which requires a very fast latency constraint. And this any node is corresponds to the button, which requires like median latency. And this is how we annotate latency constraints on this plan. And the result will be the machine that users have access to. And for the data structure, people will need to specify the mesh subplan patterns to decide whether it could be meshed to a specific data structure and the estimated size and latency. and how to eval this data structure to get the output table. And the data structure, like PVD, has its internal implemented data structures, and the users can also implement against our API to add in their new data structures. So the high-level approach is like for each interaction like plan P, and we are going to do the rule-based search to find all the candidate plans that satisfy the latency constraints. And then we will pick the best plan per interaction that maximize the data structure sharing. I will focus on the two highlighted parts in this talk. As to the plan transformation, there are three types of rules. First is the traditional transformation rules, and the choice node rules, and the data structure matching rules. And the traditional transform, we could adapt them. Like for the traditional rules, we could adapt existing database transformation rules. Like, for example, here is the predicate push down rule, which push down the hour predicate under the product filters. We could also we also define a set of choice node rules for this plan. And in this example, we could push up the any in the expression product equals to any ABC to the plan node level. And the data structure rules map the subplans that can match a data structure pattern to the data structures. And in this case, here it maps the hour filter to the B tree index on the hours. And then it can also map the aggregation and the filter to a data tile on hour, date, and sum. So this is also another plan that uses the data tile data structure. And then after this, we could enumerate the data placement by aiding the network and cloud operator at a different level. For example, the first plan will compute the scan on the cloud and do the data tile on the server and send the results to the client. And the second plan will calculate the filter on the cloud and compute and store the data tile on the server and send the final results to the client. And the third one will compute the data tile on the server and send the data tile data structure to the client and then do the query on the client. All these three have different trade-offs depending on the machine calculation speed and the machine resource availability. And after that, how to pick the best plan per interaction that maximize data structure sharing. I will use a simple example to illustrate the idea. So we just have a slider for the line chart and a static heat map. And the line chart has two possible plans. The first is the B tree on the hour, and then we aggregate. We do the aggregate on the fly. It's like 1 megabyte. And the second is a data tile on the hour, date, and the sum over the price, which is takes 3 megabytes. And however, the heat map is on date, hour, and the sum of price of as well. And the pre-computing the heat map takes 3 megabytes. Naively, if we choose the cheapest for each, we would choose the B tree and the heat map. It will end up take 4 megabytes. However, we could reuse the data tile to accelerate the heat map as well, since the data tile is capable to compute this kind of materialized view results. So if we choose the data tile only, we could only need 3 megabytes. In general, how we found such a data structure sharing opportunity is by using the integer programming, and we assign each data structure a variable and encode the problem as integer programming, which supports the data structure sharing and also decide the placement as well. So to put all of this together, given PVD with its own predefined rules, data structure, and cost, the interface designer will come up with interface with its interface data flow specification I and the client-side memory constraints and the server-side memory constraints and also the latency constraints for all the choice nodes. And he could also extend the existing rule library and data structure library to aid his customized optimization following the API discussed above. And given all this, PVD will use the rule-based search to search for all the candidates. And internally, we do some optimization like early pruning, rule priorities, work sharing, parallelization, etc. And after found the candidate, it will give to the integer programming global optimizer, and then we have the solutions for each interaction. That's the work for from the perspective of interface designer. And as the interface user, they will use the optimized execution plan, which spanning the client, server, and cloud to execute the query, and every interaction will satisfy the constraint. So we did a lot of experiments to study PVD systems, and in this talk, I will mainly talk about how does PVD compare with baseline. And for this comparison, we pick 6 representative interface on the website, like on the observable, academic papers and the Google interface, and also the public scientific database portals. And to define the latency constraints, we pick 3 kinds of latencies. L1 means that the range slider and the brush should be fast within 20 milliseconds, and all other interactions could be a little bit slow, let's say take median latency constraint 200 milliseconds, and L2 means that every interaction should be within 20 milliseconds, and L3 means that every interaction should be within 200 milliseconds. And we also propose 2 resource constraints, R1, which has 100 megabyte on the client side and 1 gigabyte on the server side. And R2 is relatively larger, which has 1 gigabyte on the client side and 10 gigabyte on the server side. And we picked the state-of-art visualization framework Mosaic and Azure with automatic tuning features as our baseline. And the automatic tuning features is actually doing the physical database design work. But we can see the results that PVD support all the settings under resource constraint 2 and 88 settings under resource constraint 1 because it can mix and match optimization, placement, and caching policy in a more flexible way than Mosaic and Azure. While Mosaic only supports up to 55 and Azure only supports 5% of settings. So to summarize, PVD is the first system that decouples interface designers from system design to provide design independence. And the key contribution include a problem formulation of PVD and a solution using the rule-based optimizer design combined with integer programming and cost estimation that allows the designer to balance latency guarantees and plan feasibility. So to conclude, I have introduced PI2, which can automatically generate interface design from analysis, and PVD, which can automatically optimize the interface to satisfy the interaction latency constraints and memory constraints. And combine this together, given the analysis, we could automatically design the interface and optimize it. So the whole interface creation process can be greatly simplified. There are still a lot of open questions in the field, like incorporating personalization into interface generation, extending the data structure operator in PVD to specialized engine operator like GPU operator, etc., which are super interesting to explore. And here are some reference for all this work. And thank you.